People of Earth, today I will share with you the knowledge of how to calculate the evolution of guitar strings. Perhaps someday I will share with you the technology required to make a mathematical program that does not crash with simple calculations, and presentation software which does not constantly lock up, because your people are badly needing those technologies. Alright, I stretch a guitar string to the shape shown below, then I let it go. Find an equation for the shape of the guitar string as a function of time. Okay, so here's my guitar string. At one end it's 0, fixed at 0. At the other end it's fixed at 0 because it's a guitar string, right? And then I pull it out to a shape where it ramps from 0 to H a quarter of the way across the string. It ramps down from H to 0 over the last quarter of the string, and the middle half of the string is just constant at H. Alright? Now, so I start with this shape. I want to find what it does in time. Well, I know I can write whatever my guitar string is doing as a sum of the harmonics on the string. Alright, and each of the harmonics has a shape which is just sine n k naught x, where of course k naught is, what is k naught? It's 2 pi over 2L, right? Remember, because my first harmonic actually has a wavelength which is twice the length of the string, so k naught is just pi over L, right? So each of my harmonics looks like this, and then it evolves. It just oscillates sinusoidally at some frequency, all right? But each of these harmonics could have a phase shift in time, all right? Another way I could write this is, instead of writing a cosine with a phase shift, I could have two different pieces where I have each of my harmonics, and there's a cosine part in time and a sine part in time. All right? Now, at time t equals 0, the sines all go to 0, so it turns out that this part of the time evolution of my string has to do with an initial velocity, not an initial displacement of the string. So we're going to ignore that. In this class, we're just going to assume that our string is not moving at time t equals 0, so we can write it like this, and we don't have to worry about any phase shifts. All right? So what we're trying to do is we're trying to write the guitar string like this, and then I know how it evolves in time. When you take Physics 318, you'll learn about this other part, what to do if your guitar string is moving at some places at time t equals 0. All right? So what we want to do is we want to basically write our guitar string like this. If I set t equals to 0, all these cosines go to 1, and what I'm really trying to do is just write my string at this like this at time t equals 0. If I can find these a sub n coefficients such that this equals the shape of my guitar string at time t equals 0, then I can just go back in and multiply the cosine part on each of my terms of my sum, and I can see how it evolves with time. So my goal is to try and find the a sub n's. I want to write the initial shape of my guitar string as a sum of the shapes of the harmonics on the string. Well, when you do Physics 318, again, you'll talk about this a lot. For now, the tool we have is the Fourier Series, where I can take some periodic function and write it like this, as a sum of sines and cosines. So what I'm going to do is I'm going to try to come up with some function that when I do my Fourier series, I get something that looks like this. So I'm going to take my guitar string. My guitar string does this, right? From 0 to L, it goes up, down. I want to imagine some repeating wave that when I do the Fourier series of my repeating wave, I get something that looks like this. All right, so I'm going to imagine that my guitar string is part of some just infinitely repeating periodic wave. Well, I might just say, well, let's just imagine that it repeats over and over again. All right, maybe that's a good option. All right, if I do the Fourier series of this, what am I going to get? Well, first of all, I've got a problem, because remember, the fundamental wavelength of the wavelength of my first harmonic on my guitar string is 2L. All right. This repeats every L, this wave repeats every L, so that means that k naught for this waveform is going to be 2 pi over L. We wanted k naught to be equal to pi over L. So we want a function that doesn't repeat every L, we want a function that repeats every 2L, so that we get the correct wavelengths for the harmonics on our string. Remember, the fundamental of our guitar string looks like this. We only fit half of a wavelength on there, right? And so it repeats every 2L. The fundamental wavelength of our fundamental on our guitar string is 2L. So we want to write a repeating wave which repeats every 2L. Also, when we do our Fourier series, we want to get something that looks like this. All right? If I have some periodic wave which looks like this from 0 to L, if if I write a Fourier series, that Fourier series will look like this from 0 to L, but we want our Fourier series to only have these terms in it. We don't want any cosines. We don't want any terms that repeat every L, right? Well, we do, but we also want to catch the 0L, all right? The 2L term. We want our, blah, blah, blah. What I mean to say is we want our lowest frequency term to repeat every 2L, not every L, all right? So we want something that repeats every 2L, and we don't want any cosines. How can we make sure there are no cosines? We make sure that our function is odd, because sines are odds, cosines are evens. So this function right here, it repeats too often. It repeats with a period of L, you know, a spatial period of L, rather than a spatial period of 2L. And it's even rather than odd. So forget that one. What we really want is we have our guitar string, it's shaped like this. We're just going to reflect our guitar string about the origin, all right? And then we're going to repeat this over and over again, all right? So that's the periodic wave we want to use to do our Fourier series. If I write this as a Fourier series, I'll get only sines and it will look like just the harmonics on the string. Okay, so let's do that. I'm going to take my wave, and my wave, I said I want something that looks like this, goes up, and then I reflect it, all right, and repeat it over and over again, all right? And to find my a sub n's and b sub n's, I'm going to do integrals, all right? Now this function, I don't really have an analytic function for the shape of my guitar string, but if I break it up into pieces, I can find analytic versions for each of those pieces, all right? Now, I'm supposed to integrate, remember, so to find b sub 0, I just integrate over one fundamental wavelength, which is 2L, all right? I take 1 over the fundamental wavelength, and I integrate over that fundamental wavelength. It's supposed to be f of x dx, right? And really, this is just the average height of my function, all right? I do this integral, and it turns out I'm going to get 0. You can go through and do this, but the point is if I integrate over a whole period, this averages to 0. All right, now that's good because I didn't want an offset on my guitar string, right? Because I wanted to write like this. This has no b naught term in it. In fact, it doesn't have any b terms. So let's look at b sub n, right? For n greater than 0, we get 2 over 2L integral from 0 to 2L f of x cosine n k naught x dx. Once again, we look at this and we say cosine is even, our function is odd, I multiply them together, I get something odd. That's going to integrate to 0. Why would an odd integrand integrate to 0? Because, remember, because of this is periodic, I can integrate from 0 to 2L, or I can shift where I start. I can integrate over any complete period. I could start anywhere and go to integrate up to 2L above that, and I'll get the same thing because it's periodic. So let's shift our integration limits to minus L to L. All right, if I integrate from minus L to L, you say, oh, look, I'm integrating this times something even, so I'm integrating an odd function from minus L to L, right? My odd function is anti-symmetric about the origin. So my integral from negative L to 0 is going to be the opposite of my integral from 0 to L, and this is all going to cancel out, and I'll get 0. So long story short, if I have an odd periodic function, all my cosine terms will go to 0. All of my b's will go to 0. All right, that's good. Now I just need to find my a sub n. And a sub n is equal to 2 over the distance I repeat over. Then I integrate, and let's integrate, like I say, from L to negative L to L rather than from 0 to L, because it's just easier to write this. If I integrate from here to here, I have to break it up into 1, 2, 3, 4, 5 pieces, but if I integrate from here to here, I only have to break it up into 1, 2, 3, let's see. For going from here to here, I have 1, 2, 3, 4, 5 pieces. But if I go from here to here, I only have 1, 2, 3, 4, 5. Oh, it's exactly the same number. Maybe if I were smart, I'd integrate from here to here, and then I only have 4 pieces. But I'm going to do a trick, all right? So I'm going to integrate. I'm going to show you why. I'm going to integrate from minus L to L, and I'm going to show you a nice trick here. All right, and then I just have to integrate f of x sine n k naught x dx. All right? So that's what I'm going to do. Okay, now the trick I'm going to use is I'm going to look at this, and I'm going to say, look, whatever this thing is, it's an odd function. This is an odd function, this is an odd function, so I multiply them together, I'm going to get an even function. Something where, if I look at what happens on this side, what happens on this side will be the same inverted. So if I integrate from minus L to L, that's the same as integrating from 0 to L and multiplying by 2. So I'm going to simplify this because I have an odd function and I'm integrating symmetrically about the origin. My trick here is, so I have 1 over L, right? But instead of integrating from minus L to L, I'll just integrate from 0 to L and multiply by 2. All right, you don't have to do that. You could just go ahead and plug your integral in and go through it, right, blindly. But I'm just saving myself a little bit of work by noting that this integrand is even. And if I integrate an even function from minus L to L, I get the same thing as 2 times the integral from 0 to L. All right, so it just made my life a little bit simpler. All right, so a sub n is 2 over L. And now I'm going to break my integral up into pieces. All right, so if I look right here, I need to somehow, I'm integrating from here to here, right? So I end up only integrating over the guitar string by using this trick, right? I don't have to integrate over any of my imaginary stuff, my pretend, what my function is doing outside of the guitar string. So that's kind of nice. All right, from here to here, what is my function equal to? It goes from 0 to h. So let's from here to here, it goes from 0 to h in a distance of L over 4. So this is just going to be 4h over L times x, right? And for this region right here, it's just equal to h. Over here, it's got the negative slope, so it's going to be negative 4h over L times x, but then I need to add in an offset, right? So that it goes to 0 when x is equal to L. So if I plug in x equals L here, I get minus 4h. So I better add 4h, so that when I plug in x is equal to L, it goes to 0. So that's what the function looks like here. This is what the function looks like here, and this is what the function looks like here. So I'll break my integral up into 3 parts. So I'll integrate from 0 to L over 4, all right? And my function is equal to just 4h over Lx. 4h over Lx, and then I multiply that by sine n k naught x dx. And then I'm going to have an integral from L over 4 to 3L over 4, and this is where the string is just constant equal to h there. Sine n k naught x dx. And then my last piece goes from 3/4 L to L, and up there my string is equal to 4h minus 4h over Lx. So 4h minus 4h over Lx. So that's what my function looks like over that last segment, and then I multiply that by sine of n k naught x dx. All right, and then I just go and do this integral. This integral is really easy. This constant comes out and I have x times sine. Go to Mathematica or look at an integral table, you can figure out how to do that. Here I once again have a constant times sine. I can break this, I can distribute this out and break this into 2 integrals. One of them is just a constant times sine, one is just, again, x times sine. So I should be able to do all of those integrals. I'm not going to go through all the tedium of doing the integrals, plugging in the limits, simplifying. Let's just jump to the end here. And what we end up getting is we find that a sub n is just equal to this. All right? Oh, and I'm using this, I switch back and forth between small h and little h, but that's the same h, okay? All right. So there is my a sub n, so I can just plug that into my sum, right? And I just remember y at x comma time t equals 0 is just the sum of a sub n sine n k naught x, right, from n equals 1 to infinity. That's my a sub n. I just plug it in and I've got my sum, all right? But notice something. I can use, I've got a sine plus a sine, and we remember this trig identity we used when we were doing beats and traveling waves. Sine of a plus sine of b is just 2 times cosine the difference over 2 times sine of the average. So if I apply that identity to this, I can write this like this. Does this look any better? Well, it's kind of cool because look at this. If n is even, sine of n pi over 2 is going to be 0, right? If n is equal to 2, it's just sine of pi. If n is equal to 4, it's just 2 pi, sine of 2 pi. If n is equal to 6, it's just sine of 3 pi, right? So what that tells me right away is a of n for even n is 0. And then for odd n, right, for odd n, this is just going to be like if n is equal to 3. So if I look at my sine, for odd n, I have 1/2, 3/2, 5/2, 7/2. So sine is just going to alternate between 1 and minus 1. So I can maybe write this as like 2n, let's see, n plus 1 divided by 2. Does that work? If I plug in n equals 1, this is 2, and I get positive. If I plug in n equals 3, that's 4/2. So sorry. If I plug in n equals 1, that's 2 over 2. That's n to the first power. So that should be minus 1. n minus 1 over 2, right? So anyway, the point is my sine oscillates as I go, right? So if let's just make a little table here. I only have to worry about the even ends, right? 3, 5, 7, 9, 11, 13. All right, for n equals 1, this is positive. For n equals 2, it's negative. It just oscillates back and forth. Positive, negative, positive, negative, positive. All right? If I look at my cosine, what does it do? All right, so my cosine, it's pi over 4. So here's 1 pi over 4. 2, right? A sub n is 0 for even, so we don't care about the even. There's 1. There's 3. There's 5. There's 7. If I take the cosine, all right, cosine of this is just root 2. Cosine of this is minus root 2. Cosine of this is minus root 2. Cosine of this is, sorry, 1 over root 2. Sorry, minus 1 over root 2. 1 over root 2. So I look at this and I say, oh, my cosine, it's just going to be, my first one is 1 over root 2. My next one is minus 1 over root 2. Then I have another minus 1 over root 2. Then I have plus 1 over root 2. Then I have plus 1 over root 2. Then I have minus 1 over root 2. Then I have minus 1 over root 2. All right? So I multiply them together and I just get 1 over root 2. And then I multiply them and I get plus, plus, minus times plus is minus, plus times minus is minus, plus times plus is plus, minus times minus. All right, so I get alternating plus, plus, minus, minus, plus, plus, minus, minus. All right? So I could come and I could simplify this and just, my whole thing, sorry, becomes just, for odd, it just becomes 16h over n squared pi squared root 2. All right, times something that alternates plus or minus every 2 odd terms. All right, and I can show this if I actually plot my a sub n with the signs and things in it. All right, those are the dots here. It's positive 0, positive 0, negative 0, negative 0. And this line right here is just plus, these two lines are plus or minus 16h over n squared pi squared root 2. And you can see the even ones are all 0, the odd ones are right on those lines, but alternating. I have 2 that are positive, and then 2 that are negative, then 2 that are positive, then 2 that are negative. All right? So we gain some insight by using this trig identity and thinking about what sines and cosines of specific angles were. But to actually write my sum, a lot of times things simplify a lot when you do these sine cosine tricks. All right? But in this case, it's a little weird to have, you know, something that alternates every 2 things. Sorry about that. I'm doing a video. I'll call you back in a minute. So something that alternates every, you know, opposite term, every 2 terms rather than 1 term. Get my focus back here for a minute. Sorry about the phone call. Anyway, the point is, oftentimes when you do those trig identities and think about, you know, when is sine positive, when is it negative, and whatnot, you can simplify your expression a lot. But in this case, it turned out it didn't really simplify it a whole ton. It got a little weird. So we'll go back to our original representation, and here it is. This was our a sub n. So here is the original shape of our string written as a sum of the harmonics on the string. I just take the harmonics. This is k naught is pi over L, right? I plug that in, plug in my a sub n. Now on my computer, I can't really sum to infinity, but if I sum it to 100, it looks an awful lot like the original shape of my string. The goal of this problem, though, is to figure out what my string is going to do in time. So now what I need to do is I just come over here and I multiply by my cosine n omega naught t, right? I multiply each term by how fast that harmonic oscillates, all right, by the cosine, you know, term that tells how it oscillates. So if I plug that in and plot it at different times, I get something that looks like this. So now I can animate, I can look and see how my string evolves in time, all right? It's periodic, it returns to its original state, and then oscillates again. The cool thing to note is kind of only interesting stuff is happening at the corners. All right, remember the wave equation said that the second derivative of time looked like the second derivative with x. So only when the slope is changing is interesting stuff happening. All right, where I've got just a straight piece of string, it just moves at a constant velocity, or a flat piece of string moves at a constant velocity or sits still. All right, but those corners, the corners are kind of where things are changing. Anyway, I found my solution. People of Earth, take this technology and use it to your advantage.